We're going to get real small here in the next couple of days and talk about the quantum level of physics. And one of the things that happens when you get small is things get really strange. So if you remember back when we talked about refraction, uh, and for a couple of slides, I said, oh, the light is getting from point A to point B the fastest way it can. Um, and we sort of glossed over the fact, well, how does the light know how to get there in the fastest way? That was just a hint of the sort of strangeness that we find when we get to the quantum level. So we're going to dig into that in the next couple of days. So what is quantum physics? Well, most of the time when we talk about the physical world, we talk about it as continuous. What does that mean? Well, it means that we assume everything can be subdivided, right? How much mass is there? Well, you can take it to as many decimal points as you want. Um, like if I say this, this mug is 0.3 kilograms, I can then say as well, it's really 0.301 kilograms. So really it's 0.30124 kilograms. And I could just keep detailing how what that mass is um, infinitely. But the truth is that that's not the case. Once I divide it down, my mass down 100 times, I take a cup of water, um, I divide it in half, and I divide it in half, and I have less and less water. At some point, you can't divide it anymore. You have a molecule of water, um, and you can't have a fraction of that molecule. It's either one or none, and that's the world of quantum physics. When we start getting down to a place where you either have something or you don't, rather than having a fraction of it. Now we understand that with molecules, but it actually applies to a lot of the other things that are going on at the quantum level. So something quantized is something that has to be counted with integers. I have 6 molecules. I can't have 6.2 molecules. So why is that so important? Well, it tells us something about the world at that very, very, very small level. Um, because not only can molecules and particles be quantized, but things like energy can be quantized. Um, so what does that mean? Well, atoms can be imagined as oscillators that are absorbing and emitting radiation. So we remember that energy is motion, and so the thermal energy of molecules is them moving back and forth. But they have charges and magnetic fields, so that creates EM waves. And so you have EM waves coming in and out of molecules all the time. Um, but the odd thing about this is that as your radiation changes energy levels at a given frequency, if your frequency stays the same, the atoms jump from one energy level to another instead of gradually moving. So well, okay, what exactly does that mean? Well, let's think about the energy that's radiated by an oscillating particle. So here we have E equals NHF. N here, N is the number of photons that are being emitted. H is a constant called Planck's constant, and it's tiny, as you can see there. And then frequency is the frequency of oscillation. So our atom is oscillating at a given frequency, right? That's what we declared up here. So this stays the same. This stays the same. If we want to think about the energy radiating, it has to be an integer multiple of HF. In other words, when we talk about it radiating energy, is it radiating 1 photon or 10 photons or 14 photons? It can't radiate 1.5 photons. And so this is where energy becomes quantized. The amount of energy being put off as an electromagnetic wave can only be counted in terms of an integer multiple of that HF. So this leads to what's called the photoelectric effect. And this was actually how people figured out that the energy is quantized at these levels. So what happens, we have a little atom over here. What happens when light strikes that material? Well, that means photons, these little particles of light energy, are coming into the atomic structure. And if they hit an electron, they can eject that electron from the orbit, okay, or the space, this atomic space here. But you need a certain amount of energy to do that, right? Because there's a bonding force holding these here. And so to give this enough kinetic energy to leave this space, you need a certain amount of energy. This is called the photoelectric effect. So light strikes the material. This means that photons, each carrying a certain amount of energy, right? H, our Planck's constant, times the frequency of that photon, are bombarding the surface. The electrons are held in place by a binding energy. And then we have to think of those individual photons interacting with individual electrons. That photon, the binding energy of the electron here is a certain level. It needs a certain amount of new energy to get out of this atomic structure. If that photon, that individual photon, doesn't have enough energy to do that for the electron, then no electrons will leave this space. In other words, if the frequency of the light is too low, if each photon has not enough energy, no electrons will be ejected. The photon energy is not enough to break the binding energy. What does that mean? It means that you're not just sort of slowly building up energy that's going to make this electron leave. What you're doing is one photon is interacting with one electron and transferring its energy. And only if the energy of that photon is enough to break the binding force of this electron will the electron be able to leave that atomic structure. So if the frequency is high enough above, and we can see this equation here is just in a rearrangement. HF is our energy of the photon. Binding energy is the energy needed to release an electron. If HF is greater than or equal to BE, then some of those electrons will be freed. Okay, so here that frequency, since H is a constant, we can move it to the other side. There's an initial frequency essentially where your frequency of the electron has to be high enough in order to break that binding energy. Then we can calculate the kinetic energy of if you're of the leaving electron. If that photon contains just enough to break the binding energy, the electron's going to leave, but it's not going to have very much kinetic energy. Any extra energy turns into kinetic energy for the electron. So an electron that breaks the bond and flies away might have a great deal of kinetic energy if you have a really high frequency. If we just thought about this in terms of a wave theory, we would think that if we just had a low frequency light that was really high intensity, that had a lot of power behind it, we would be able to free electrons, right? You just hit that electron with a wave that's strong enough. And even if the frequency isn't that strong, eventually you would give that electron enough energy to leave. But that's not what happens here, right? So that wave theory falls apart here, and we have to think about this light as individual photons hitting individual electrons. That's what makes, that's why quantum physics is different than continuous physics, than Newtonian physics. All right, so then we can go back to our EM spectrum and think about that energy of a photon, E equals H times F. And now we can see that the right side of this spectrum, where our frequencies are much higher, right? The orders of magnitude are huge here, 10 to the 20th as compared to, say, 10 to the sixth over here, um, is a ton more energy in a photon of a gamma ray than a photon of a radio wave, right? And an X-ray here has 1,000 times, let's see, we're about 10 to the 15th here. So an X-ray right here has 1,000 times more energy, a photon, than a photon in the visible range. That means that high energy waves, high frequency waves like UV waves and X-rays and gamma rays are dangerous and useful. They can ionize materials by freeing electrons. That's the photoelectric effect, right? They have enough energy that when they hit an electron, the electron can leave that atomic structure. But that also means that they can damage cells, they can cause cancer, and they can penetrate materials like a diagnostic X-ray.